On a clear night, the Milky Way looks like the center of everything. Stars packed together, galaxies scattered around us in every direction. Our neighborhood of the universe looks orderly, balanced, almost calm. But look a little deeper into the data, into the actual velocities of the galaxies around us, and something is deeply wrong. Almost every major galaxy near us is leaving, not drifting randomly, not orbiting, leaving. You clicked because something invisible is wrapped around our galaxy. By the end of this video, you'll understand why that one discovery solves a mystery astronomers have been fighting over since before your parents were born. Here's the setup. The universe is expanding. We've known that for nearly a century, ever since Edwin Hubble watched galaxies recede in every direction. And that expansion should carry everything apart at a rate proportional to distance. Farther away means faster recession. Fine. But the Milky Way and the Andromeda Galaxy are a dramatic exception. Andromeda is hurtling toward us at roughly 110 kilometers every second. Our two galaxies are gravitationally bound, locked in a slow-motion collision that will play out over the next 4 to 5 billion years. So we're heavy enough to hold Andromeda. The Milky Way and Andromeda together contain somewhere around 2 to 3 trillion solar masses of matter, most of it dark. That's an enormous amount of gravitational pull, which means the galaxies just outside our neighborhood, say 3 to 10 million light-years out, should at least feel that pull. They should be moving away a little slower than the rest of the universe, dragging their feet. That's because our combined gravity should be tugging them back. But they're not dragging their feet. They're receding at almost exactly the speed you'd predict from the universal expansion alone. It's as if the Milky Way and Andromeda, with their combined mass of trillions of suns, are gravitationally invisible to the galaxies just a few million light-years beyond them. Astronomers have a name for this: the quiet Hubble flow. The nearby expansion is suspiciously smooth, suspiciously orderly, suspiciously unaffected by the largest concentration of mass in the local universe. And for 50 years, it has made no sense. How do you weigh 3 trillion suns of matter and then watch the neighbors act like you're not even there? What if everything we assumed about the shape of our cosmic neighborhood was wrong? To understand why the quiet Hubble flow is so strange, we need to rewind to the late 1950s. In 1959, two physicists, Franz Kahn and Lodovic Volter, asked a deceptively simple question. If the Milky Way and Andromeda started out moving apart after the Big Bang, carried by the universal expansion, what could possibly have reversed Andromeda's course and sent it falling back toward us? Their answer was gravity, pure Newtonian attraction. But when they set up the math, using the current distance between the two galaxies, Andromeda's approach speed, and the age of the universe, they found something that nobody expected. The gravity required to reverse Andromeda's path was enormous. The local group had to contain at least 10 times more mass than all the stars and gas astronomers could see. In 1959, nobody called it dark matter, and Kahn and Volter thought it might be hot intergalactic hydrogen, invisible to optical telescopes, but massive enough to bind the group together. But the deeper implication was inescapable. The visible universe is the tip of a gravitational iceberg. Most of the mass holding our cosmic neighborhood together is invisible. This calculation, known as the timing argument, became one of the earliest and most elegant pieces of evidence for hidden mass in the universe. It's a beautiful piece of physics. You watch two objects approach each other. You know how far apart they started and how long they've been traveling, and you work backward to figure out how much mass is pulling them together. Like weighing an anchor by watching how fast a boat slows down. Over the following decades, the timing argument was refined and updated. modern versions. Using better distance measurements and more sophisticated orbital models put the total mass of the local group somewhere around 4 to 6 trillion solar masses. That's a lot, but here's the part that should make you uneasy. Does that number match what other measurements say? Cosmic Tide viewers know to ask this question, and the answer is no, not even close. When astronomers weigh the Milky Way and Andromeda individually, using the orbits of their satellite galaxies, the rotation speed of their disks, the motions of stars in their halos, the answer they get is consistently lower. Add the two galaxies together, and you get roughly 2 to 3 trillion solar masses, maybe 3.5 if you stretch the error bars. So the timing argument says 4 to 6 trillion. The internal measurements say 2 to 3. That's not a rounding error. And that's nearly a factor of 2. For decades, this gap sat in the literature like a bone stuck in the throat of local group dynamics. Either the timing argument was overcounting mass, perhaps because it treats the Milky Way and Andromeda as isolated point masses when they're clearly embedded in a larger environment, or the internal measurements were undercounting, or something else entirely was off. And the quiet Hubble flow only deepened the problem. If the local group really contained 4 to 6 trillion solar masses, nearby galaxies should feel that gravity. Their recession should be measurably slower than the cosmic average. But the data showed the opposite. The local expansion was eerily smooth. Previous models tried to fix this by stripping away most of the dark matter beyond the halos of the two main galaxies, and reduce the surrounding mass to almost nothing, and the recession speeds start to work. But that fix created new contradictions. It clashed with the timing argument, and it didn't match the dark matter content predicted by the standard cosmological model. Something in the geometry of the problem had to be wrong. But what exactly? Park that question for now. We'll come back to it. First, there's another clue hiding in our cosmic backyard. One that involves a truly enormous region of nothing. In 1987, astronomer Brent Tully and his colleague Richard Fisher noticed something peculiar about the arrangement of galaxies near the Milky Way. Our galaxy sits inside a thin, remarkably flat arrangement of nearby galaxies, a structure they named the local sheet. Think of it as a cosmic tabletop, and with our galaxy and its immediate neighbors laid out across a plane. And on one side of that tabletop, there was almost nothing. They called it the local void. And it's not small. Imagine a region of space at least 150 million light-years across, almost entirely empty of galaxies. No major structures, no bright clusters. Just vast, echoing emptiness stretching in one direction from our galaxy, hidden from direct view by the thick dust lanes at the center of the Milky Way. Here's the thing about voids. They're not just empty patches. In a gravitational universe, a void is an active structure. Matter on the edges of a void gets pulled toward the nearest dense region, away from the void center. As matter evacuates, the void grows emptier, and its influence on surrounding galaxies grows stronger. It's not gravity pulling you in. It's the absence of gravity letting you fly away. In 2007, Tully found a lonely dwarf galaxy adrift inside the local void, and it was fleeing the void's center at roughly 350 kilometers per second. That's not a gentle drift. That's a sprint, and the speed is telling. For a galaxy to escape that fast, the void has to be enormous. Its gravity so weak, so diffuse, that nothing inside has any reason to slow down. But the real shock came in 2008, when Tully's team decomposed the Milky Way's own peculiar velocity, our galaxy's deviation from the smooth cosmic expansion, into 3 separate components. The largest was a pull toward distant galaxy concentrations near the Centaurus region, around 455 kilometers per second. An intermediate component came from the gravitational tug of the Virgo cluster at about 185 kilometers per second. And the third? The local void was pushing us away at 259 kilometers per second. Let that sink in. Our galaxy, a disk of hundreds of billions of stars wrapped in a dark matter halo weighing over 1 trillion solar masses, is being shoved through space by the absence of matter beside it. Not pulled by something massive, pushed by nothing. Now here's the part that matters for our story, the thread that connects the clues. Tully had identified 2 structures that nobody could quite fit together. 1, the local sheet, a flat plane of galaxies. 2, the local void, a vast emptiness bordering that plane. The Milky Way, Andromeda, and the entire local group were embedded in that sheet, sitting right on the boundary between structure and nothingness. If you only read the headlines, you might think these were separate curiosities. Interesting, but unrelated. The quiet Hubble flow over here, the mass discrepancy over there, the local void off to the side. But cosmic tide viewers know to look for the thread that connects them all. And in January 2026, a team at the University of Groningen finally pulled that thread tight. Wempe was a PhD student at the Captain Astronomical Institute in Groningen, the Netherlands, working under Professor Amina Helmi. Their collaboration included researchers from Germany, France, and Sweden. And their goal was extraordinarily ambitious. Build a digital replica of the local group so accurate that it reproduced not just the Milky Way and Andromeda, but the positions and velocities of 31 individual galaxies in the surrounding volume, out to about 13 million light-years. Not a statistical average, not an approximation, a match, a simulated universe that moved like ours. The tool they used is called BORG, Bayesian Origin Reconstruction from Galaxies. It's a computational framework that starts from the cosmic microwave background, the faint afterglow of the Big Bang that encodes the density fluctuations of the early universe. BORG takes those fluctuations and generates possible initial conditions, plausible starting arrangements for matter in a small patch of the early cosmos. Then, it evolves each arrangement forward through 13.8 billion years of gravitational collapse, dark matter clustering, and structure formation, using a high-resolution simulation code called Gadget 4. The crucial innovation was the constraints. Most cosmological simulations model a generic, randomly selected region of the universe. Wempe's team didn't want generic. They forced every simulation to produce a local group analog. 2 galaxies with the right masses, the right separation, the right relative velocity, surrounded by 31 galaxies at the right positions, moving at the right speeds. If a simulation didn't match the observations, it was discarded. They ran 169 of these constrained realizations. Each one began from slightly different initial conditions, consistent with the cosmic microwave background data. And across all 169 successful simulations, a striking, consistent pattern emerged. The mass surrounding the local group wasn't spherical. It wasn't randomly distributed. In every successful simulation, every universe that actually reproduced what we observe in the real sky, the dark matter beyond the Milky Way and Andromeda, was organized into a vast, flat sheet. This sheet extends at least 32 million light-years in every direction within its plane. At its center, the density of matter is roughly double the cosmic average. And above and below the sheet, almost nothing. Deep voids, dramatically emptier than the rest of the universe. Picture an enormous dark pancake, tens of millions of light-years across, made almost entirely of invisible matter. The Milky Way and Andromeda are embedded inside it, like raisins in a cosmic flatbread. Above you, void. Below you, void. and all around you in the plane, a dense, invisible scaffold of dark matter stretching farther than any telescope has ever imaged in a single exposure. This geometry wasn't assumed. It wasn't fed into the simulation as a starting condition. It emerged organically from the mathematics of gravitational collapse. That the only way to reproduce the real motions of the galaxies around us, within the framework of standard cosmology, was for the dark matter to arrange itself in this flattened architecture. Wempe described the result as the first detailed assessment of the distribution and velocity of dark matter in the regions surrounding the Milky Way and Andromeda. Not the first guess, not the first approximation, the first assessment grounded in a simulation that actually reproduces what we observe. His supervisor, Amina Helmi, put it more personally. Astronomers had been trying to solve this problem for decades, she said. And now, based purely on the motions of galaxies, they could finally determine a mass distribution that matched both the positions and the velocities of galaxies in and around the local group. And here's what makes this result land like a hammer. Once you see the sheet, the 50-year-old mystery doesn't just weaken, it dissolves completely. Remember the quiet Hubble flow, the puzzle we parked earlier? Here's why it refused to go away for half a century, and why it collapses now. Every previous model of the local group's environment assumed, more or less, that the mass around us was spherically distributed. That's a reasonable first guess. Dark matter halos around galaxies are roughly spherical. And in a spherical geometry, there's an elegant rule from Newtonian gravity called the shell theorem. Only the mass inside your orbital radius matters. Everything farther out cancels itself through symmetry. So if you're a galaxy sitting 4 megaparsecs from the local group, and the mass distribution is spherical, and then only the mass inside that 4 megaparsec sphere pulls you inward. The math is clean, the physics is textbook, but it always produced the same frustrating result. The local group was either too heavy to explain the smooth recession of neighbours, or too light to explain why Andromeda is falling toward us. A flat sheet breaks the shell theorem completely. In a flattened geometry, the mass farther out in the plane doesn't cancel. It still exerts a gravitational pull, but the pull is sideways and outward relative to a galaxy sitting near the centre. Instead of neatly cancelling through symmetry, the sheet's extended mass tugs on tracer galaxies in a way that partly counteracts the inward pull from the central concentration. Think of it this way. In a sphere, all the gravity points inward toward the centre. In a sheet, gravity in the plane points both inward and outward, depending on where you are. The net effect is that galaxies embedded in or near the sheet feel less inward pull than they would in a spherical model with the same total mass. This means the local group can have a combined mass of 3.3 trillion solar masses, exactly what Wempe's simulations found, with an uncertainty of about 0.6 trillion either way, and the nearby galaxies can still recede smoothly. The sheet's geometry redistributes the gravitational force, producing precisely the quiet Hubble flow that has baffled astronomers since the 1970s. And now, the old mass contradiction finally makes sense. The timing argument, which treats the Milky Way and Andromeda as an isolated pair, then gave 4 to 6 trillion solar masses because it was absorbing the effect of the sheet into an inflated mass estimate. Internal measurements gave 2 to 3 trillion because they only measured the galaxies themselves. Wempe's result, 3.3 trillion, sits right between them, and the difference is entirely explained by the geometry that previous models ignored. The mass was never wrong. The assumed shape was. What about the local void? That fits too. The deep voids above and below the sheet in the simulations correspond precisely to the local void that Tully mapped observationally. The void isn't a random fluke of galaxy distribution. It's the structural complement of the sheet. Where matter piles into a flat plane, the surrounding volume empties out. One demands the other. And the local sheet, that thin. A flat arrangement of galaxies that Tully and Fisher noticed back in 1987. It's a visible tracer of the underlying dark matter architecture. The galaxies mark the plane because they formed where the dark matter was densest. The sheet of light follows the sheet of dark. Step back for a moment and appreciate what actually happened here. A team of 5 researchers used the measured motions of just 31 galaxies to reverse engineer the invisible structure of our cosmic neighborhood. No telescope directly imaged this dark matter sheet. No particle detector captured a dark matter signature. They inferred the shape of the unseen entirely from the movements of the seen. That's the power of constrained simulation. You don't need to see the dark matter if you can accurately model the gravitational fingerprint it leaves on everything around it. The dance of the galaxies tells you where the invisible mass must be. And the result connects to something much larger. Cosmologists have known for decades that the universe, on its grandest scales, is organized into a web, an intricate network of dark matter filaments and sheets connecting dense clusters of galaxies with enormous voids in between. This cosmic web is one of the most striking predictions of the standard cosmological model, and it's been confirmed by galaxy surveys like the Sloan Digital Sky Survey and by large-scale simulations like the Millennium Simulation. What Wempe's team showed is that this web doesn't just exist on billion light-year scales. It sculpts our own backyard. The local sheet, the local void, and the quiet Hubble flow. They're all local expressions of the same cosmic architecture that governs the entire observable universe. The same forces that built the largest structures in creation also shaped the neighborhood you're sitting in right now. And there's something almost poetic about the method. The cosmic microwave background, light from the very first moments of the universe, which encoded the tiny density fluctuations that would eventually grow into everything we see today. Wempe's team took that primordial blueprint and ran it forward. 13.8 billion years of gravity doing its patient work, and the simulation produced a recognizable portrait of our home. The beginning of the universe, it turns out, already contained the instructions for the sheet we're embedded in. We just couldn't read them until now. We're not looking at the cosmic web from the outside, like observers studying a map. We're inside it, embedded in one of its sheets, sandwiched between 2 of its voids. And we didn't know the shape of our own neighborhood until a PhD student in the Netherlands let a computer figure it out. There's something both humbling and exhilarating about that. We've mapped galaxies billions of light years away. We've decoded the afterglow of the Big Bang itself. But the geometry of dark matter within 30 million light years of our doorstep, our immediate cosmic block, was invisible to us until 2026. So where does this leave us? Let's separate what we actually know from what's still uncertain. From what we know, the motions of nearby galaxies can only be reproduced within the standard cosmological model if the mass distribution around the local group is strongly concentrated in a flat plane, with deep voids above and below. The combined mass is about 3.3 trillion solar masses. This sheet geometry resolves the quiet Hubble flow, reconciles the timing argument's mass discrepancy, and aligns with the independently observed local sheet and local void. What's still uncertain? This result comes from one team, based on simulations constrained by 31 galaxies. 31 is not a large sample. The distances and velocities of those galaxies carry their own measurement uncertainties. And the simulations, while state-of-the-art, rely on the standard lambda CDM model being correct at these local scales. And if something about the standard model is slightly wrong, if dark energy behaves differently on small scales, or if dark matter has properties we haven't accounted for, the precise shape of the sheet might shift. Future observations will sharpen the picture significantly. The Vera Rubin Observatory, scheduled to begin its primary survey soon, will catalogue billions of galaxies and map dark matter distribution through gravitational lensing across enormous volumes of space. If the sheet and void geometry holds up in the Rubin data, it becomes a confirmed structural feature of our cosmic address. If it doesn't, the models will need to be rethought. There's also a broader, more provocative question lurking here. If the local group's dynamics are shaped so profoundly by the geometry of the surrounding dark matter, how many other galaxy groups across the universe sit in similar flat environments? Are most groups embedded in sheets, or are we unusual? Wempe's simulations suggest the former, that this is a generic feature of how the cosmic web builds itself. But proving that requires studying other local volumes with the same level of precision. And then there's the deepest question. What is dark matter? This study tells us exquisitely well where it is and how it's shaped. It tells us absolutely nothing about what it's made of. The sheet is invisible. We infer it entirely from gravity. The particles, if they are particles, remain undetected. If dark matter turns out to be something other than the cold, weakly interacting substance that the standard model assumes, the story of the sheet might change. But for now, the gravitational evidence is compelling. The picture today is more complete than it has ever been. The Milky Way is not floating in a uniform ocean of dark matter. It's lodged inside a vast, flat architecture of invisible mass, flanked by emptiness, connected to the cosmic web that stitches the universe together. Think about what that means for every other measurement we make from inside this structure. The distances we calculate to nearby galaxies, the expansion rate we infer from local observations, the mass estimates we assign to our own galaxy. All of these depend at some level on assumptions about the environment we're embedded in. And for 50 years, that assumption was wrong. We assumed spherical. The universe delivered flat. This won't be the last correction. As surveys get deeper and simulations get sharper, the invisible scaffolding around other galaxy groups will come into focus too. The Wempe paper is a proof of concept. You can map dark matter at megaparsec scales using nothing but the movements of a few dozen galaxies. That technique will only get more powerful as the data improves. And the galaxies next door, they were never ignoring us. They were responding to a structure so large, so subtle, and so perfectly balanced that it took 50 years, 169 simulated universes, and a Bayesian framework named after a Star Trek villain to finally see it. The universe is not just stranger than we assumed. It's more structured, more layered, more architecturally precise. And the fact that 31 galaxy velocities can reveal the hidden geometry of our cosmic neighborhood, that's not just a data point. That's one of the quietest, most elegant detective stories in modern astronomy. This is Cosmic Tide. Stay curious, stay skeptical, and the next time someone tells you the universe is mostly empty space, remind them the emptiness has a shape, and that shape just told us where we live.